Okay, so this is week 10, and we will just cover some, I guess, miscellaneous topics here. There's, I guess, I'll just say it like, I won't put week 10 stuff on like the final exam or things like that. And I know, okay, and then some of you have contacted me about final exam time conflicts, and I still have to kind of schedule another makeup time, but I've seen your messages and I will respond. I'm sorry, it's just haven't gotten there yet. Yes, question.
Yeah, I wanted to ask, do you have any suggestions for like good ways to study for the final? It's just for me, it's kind of like a different style class.
Yeah. So the final exam, I haven't detailed everything out yet, but it'll be a little bit like a homework assignment, but it will be kind of timed where I will say like, okay, here's this thing, and I need you have to do this, and you have to do this, and probably the hardest part is just that you have to complete it within the allotted time, and so. I guess it will be done, kind of at home on the computer, and so it will be open note, open book, I guess, open internet, really, just no messaging each other type of thing, but I would say see if you can redo some past homeworks, kind of. At least, some of those smaller tasks, without too much outside help. I mean, you're not forbidden from using outside resources or looking at documentation or things like that, but just, I guess, becoming familiar with the vocabulary and familiar with like what kind of functions are available for your use, right? So there will probably be a decent number of things using pandas, where you'll have to, like if you look at homework 4, can you get through homework 4, fairly quickly, or you can try to ask, there's probably other questions you could be asking. Can you, and then I'll probably have a little bit of stuff on like. Maybe a little object-oriented stuff, maybe like write a short function here and there. Probably a lot of like, I don't know, simple text operations like extract this string or, split something up or something. So I guess, as with learning any language, whether it be a computer language or a foreign language, the two main aspects are, the grammar and syntax, and then as well as the vocabulary. And, both are important, and both kind of develop with more frequent use. So, I guess I'll probably give you a, more detailed description of the final exam. I don't know, either Wednesday or Friday. Yeah. Yes.
Oh, are we gonna be tested on SQL though?
No, I won't put SQL on there. It will be, Python, and then as far as libraries or packages with Python, you'll have NumPy, Pandas, Matplotlib.
And classes.
Yeah, but that's part of base Python. Yeah. So basically, like base Python. So like your functions, writing a function and handling lists and dictionaries and strings and, iterables and, whatever, classes, that kind of, all of that kind of stuff. So, but, the challenge for me when I write it is writing something that is reasonably challenging but can be completed within the time frame. I know the homeworks, they can take a long time, so certainly it has to be a lot shorter than a homework, but but I also want to kind of cover a range of topics. So that's the challenge. It's like I write a problem and I'm like, maybe I got to cut this, or maybe I got to. So that's what I'll be doing. But anyway, yeah, this week we'll take a look at just a couple. Today we'll look at stats models, and then Wednesday we'll look at scikit-learn. There's probably enough like scikit-learn stuff. I mean, there's a ton of scikit-learn stuff, and maybe I'll just touch on it Wednesday, maybe Friday. I don't know. We'll see. But I hesitate to get too far into it because this is technically a lower division class, Stats 21, and so a lot of you have not taken like the 102 series. But then again, like looking at you guys, I know a lot of you have taken the 102 series. So, some of the stuff I talk about, you might not necessarily have a framework to kind of place it. Whereas if you have taken courses in like the 102 series or 101 series, you would have been exposed to at least something similar, analogous, at least in R. And this would just be kind of like, okay, well, these are the tools that are available to kind of make something similar happen in Python. And yeah, so okay, so here this is what we'll take a look at. So yeah, if you haven't figured it out, Python is this general purpose programming language, which contrasts it to R, where R kind of from the very start was designed with statistics in mind. So within R, you don't have to load any outside packages or anything, and there's the functionality to fit linear models and perform t-tests and create plots and calculate different I guess coefficients and residuals and all of that kind of stuff, right? I guess it's all of those things are technically inside the package stats, which gets loaded as soon as you start up R. So there's a lot of those kind of tools right from the get-go. Whereas in Python, people have created these packages or these modules that we load in, and it has really extended Python's general purpose programming, and has given it the array and the data frame, which now allows it to as a solution and a way for us to interact with data. Today I want to look at this package stats models. And stats models would be the package that we use for kind of traditional statistics. So things like fitting a linear model, so like linear regression, you'd use stats models, or logistic regression, anything kind of like that. Stats models would probably be your tool to use. Versus scikit-learn is really designed around machine learning. Now, technically, you can still fit linear regression models and logistic regression models and those kinds of things in scikit-learn. But all of the tools in scikit-learn, the way you verify and validate a model is through cross-validation, versus in like linear regression over here, you'd validate your model by kind of checking, your residual plot, or your, or you do model selection using the F-score or the, A1C, or AIC or BIC values or things like that for model selection. Versus in machine learning, you kind of move away from those those metrics and use cross-validation. I'm not sure if you guys have taken 101A. 101A is the kind of intro to linear regression, and multiple linear regression, that kind of stuff, where you do talk about a lot of the kind of the 101A would be kind of your traditional approach for a linear regression, where you look at, what are your model assumptions and things like that. So I am assuming we have fit at least simple linear regression, where we estimate a slope and an intercept. But I can't cover everything here. But anyway, the way you interact with stats models is there is something called the Stats Models API, and there is the Stats Models Formula API. And both of these allow us to interact with stats models. The convention is stats models is SM, and the API, the formula API is SMF. API just means how do you interact with the code. I don't know. Pretty much everything is an API. Like in terms of like if there's a way for you a human to communicate and interact with it, that's kind of like an API. And we often think of this as like, oh, how do we get my computer to talk to this website, and the website might offer little APIs or something like that. But it's basically, I don't even know what does API stand for. Just some kind of application programming interface. Okay, yeah. Or the American Petroleum Institute. Okay, but is a way for two or more computer programs to communicate with each other. Okay, so it's basically, yeah, just how do you interact with it, right? Okay, so the Stats Models Formula API gives us a format to put formulas in a way that's a little bit reminiscent of R. So in R, when you do linear models, you do like y tilde x and things like that, and that's how we would kind of go about it. Let me go ahead and just show you a very, very, very minimal example. So here I have two arrays. X is 1, 2, 3, 4, and Y is 2, 6, 4, 8. And I'm just going to show you a plot of this. Okay, so these are our 4 dots. So X is, the points are X is 1, Y is 2. Then we have 2, 6, 3, 4, and 4, 8. These are, our X values and our Y values. And I will kind of join the two together into a data frame. So, creating a dictionary, and I title this column X and this column Y. I've already plotted this. Seaborn also kind of has their linear model plot, and it shows you the dots, and it shows you also a slope, as well as like kind of this confidence interval thing. Again, Seaborn, and you might be like, oh, well, why don't we just get the slope and intercept from Seaborn? But again, Seaborn doesn't even allow you to extract the slope and intercept. It's a tool for visual exploration, but not, you can't use it to do anything. Okay, well, so how do we fit a linear model? Okay, we're going to use the Formula API, and within the Formula API, there is the function that will allow us to fit ordinary least squares, and there's kind of a big list. So let me do stats models, and we'll go to the reference, and where is so within the Formula API, these are kind of the different models that you can fit. Probably GLM and OLS being probably your most common things, and then there's I don't know what these other forms of regression are, honestly, but they haven't put in quite a bit, and so and then you're just kind of if you don't use the formula API, you have OLS and all of these things. You have to be careful because unfortunately, statsmodels.api, so this is kind of the quote normal way to interact with stats models, uses all caps OLS, but if you do the formula API, it's all lowercase. So everything with the formula is all lowercase. And it's just maybe that's just like as a double check, so you don't accidentally use one over the other. But anyway, in our case, we have this data frame, and we're going to do predict y based on x. So we do y tilde x, and we say the data comes from D, and that creates a model object. And if you say what is this thing, it says we have an OLS regression model. So we have a model object, and in order to get your coefficients, you have to call the fit method on this model object. So we do model.fit. Okay, and now we get a linear regression results object, or it's a regression results wrapper object. And to look at what's inside the regression results wrapper object, we'll call the summary method. So I'm going to do results.summary, and then we'll print this out. Okay, and the results.summary. Okay, it just gives me a warning that I only had 4 observations here, but it kind of prints out this whole table, and it says, your intercept is 1.0, the slope or coefficient associated with the x variable is 1.6, and it gives us kind of, t values and, the p values associated with these things, and a whole bunch of other stuff, right? Number of observations and the degrees of freedom, and, all of these kinds of things, your R-squared values and stuff. So this is, that's how you would kind of fit a linear regression model. And again, probably your best resource here will be to use the reference. Okay, so here I'm the stats models formula API OLS reference, and this is it returns the model instance and whatnot. Okay, let's the API reference. Yeah. Okay, so that's how you do that. Here, I can create a plot. There, one is the AB line plot, and beyond that, I can add, basically add the points using a scatter plot. I can adjust this x limits, y limits, and I'm going to do plt show, and all this does basically just adds the fitted line here. Okay, you can also ask, give me kind of your ANOVA table. So again, if you're familiar, if you've taken like 101B where you cover the ANOVA table, this will look familiar, and if you haven't, then that's okay. This is something you'll see. So this is kind of your ANOVA table where you break down your sum of squares into the model sum of squares and your residual sum of squares and things like that. And then you can also call after you fit the model. So these are all using calling different functions on the results object after we fitted the model. We can also call the predict method, and we just provide a dictionary of, say, values associated with each variable. So right now there's only kind of one input variable, and we can say, okay, what's your prediction if you put in 2? And it says, okay, we would predict 4.2, right? So if you go into 2, this point right here has a value of 4.2. the actual value in our data set is 6. That's a, residual of 1.8 or something like that. Okay, so that is the kind of the most basics of it. Let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter A. A as an apple. That's that. Okay, let me show you how to use the NumPy array notation. So when we take a look at, say, sklearn, pretty much all the sklearn functions, they fit models using the NumPy array notation. Basically, we create a matrix for our predictors, and then we have a matrix of our predicted values, y. So right now, x is just a vector, 1, 2, 3, 4. And what we want to do is we want to say, okay, y is the result of kind of multiplying x times like a array or a matrix of coefficients. And so in this case, I'm going to take my single array x, and I'm going to add a column of 1s. Okay, and this allows, so basically I just have a column of 1s and the column 1, 2, 3, 4. And this allows me to express the notation, express, kind of our values as the result of a matrix operation. So normally we would just kind of say, okay, to predict y1, we would take our intercept plus our slope times x1, and then maybe some residual error. And what we're going to do is we're going to say, okay, you know what, I'm going to gather my intercept and my slope, my beta 0 and my beta 1, into a matrix beta. Okay, so beta is like a 1 by, I don't know what I should do here. So we'll say beta is equal to, I guess, beta 0 and beta 1. I think I need to, do I need to escape these? I don't know how to do this. Okay, so you have, beta 0 and beta 1, and then basically your x will be this. And so if you think of x as a column of 1s and the values xi, then you can see that beta times x will produce the predicted component, right? So if I do that, I'll get rid of the. Okay, so y hat can be expressed as this, and x would be, our. Here you have it like this. Okay, so in this case, if we have this, then to interact with the stats model's kind of traditional, not traditional, but the stats model's non-formula API. All right, so y is an array, 2, 6, 4, 8. We're going to just say, okay, we're going to predict y using our matrix x, and our matrix x is the column of 1s and 1, 2, 3, 4. And basically, stats models is going to find a coefficient for each column in your x matrix. Okay, So again, we initialize the model, and then we call the fit method on the model. And now that we have that, we have we have the exact same results. Okay, which makes sense because we have the exact same data, right? So we have the same y values, we have the same x values, we have the same kind of intercept and slope values as predicted by the model, but that's what we have there. Okay, and so here the variable names though, it says constant and x1, and as far as constant, because we use add constant, it recognizes the first column as constants and the second column as kind of your x1 variable. Whereas back here, it named it the intercept and the x using the kind of the formula API. That's the only real difference there. I don't know when you guys cover this, 100C maybe, where you have the solution to ordinary least squares regression is x transpose x inverse x transpose y. That we could solve it using this. And again, if you haven't taken any of these these courses, 100C or whatever it is, it'll come later. Okay, but if we wanted to show this, we could do x transpose x here. X transpose, so x dot t matrix multiply uses the @ sign in Python. So x transpose t times x, x transpose times x. That's what we have. X transpose x. The inverse function is linear algebra dot inverse. So that's going to be x transpose x inverse, and then multiplied by x transpose y. And if you do that, you get a matrix with the coefficients 1 and 1, or the values 1 and 1.6, which correspond to your coefficients here as well, 1 and 1.6 here. Okay, I'm going to just do one more example using stats models. This one I'm basically taken straight from here. So the stats models website, the kind of the reference documentation, there is quite a bit of some good examples here. So if you click examples, I'm going to look at just ordinary least squares as a thing, but there's a whole bunch of these other things. Maybe I should have done something from regression diagnostics, but other things, kernel density estimation, lowest regression, lots of stuff. We just don't have time for any of this, really, to go over everything. Time series analysis. Do we still have a time series class, right? As an elective? No? Maybe? There's we're just strapped for finding faculty to teach all of these different electives and stuff, We have I enjoy teaching the core series of classes, like the 102 series, but then right now I'm also the only one teaching like this Python course, so we need more teachers. It's hard to find good teachers though, and to say, hey, don't take that job in industry. Come work for the university. It can be a tough sell sometimes, But anyway, here we are. Okay, so here we're going to just generate some random data. What I'm going to do is I'm going to start by. Are we able to read this code? What's happening here? 0, 10. So what is this going to produce from NumPy? Produce an array, length 101, starting at 0, ending at 10. And so x is going to be 0, 0.1, 0.2, 0.3, 0.4, all the way up to 10. Okay? And then column stack, we're going to have a column of basically x, and then a column for x squared, taking that value. So if we look at the first value, first 6 rows, right? And then are we accustomed to like NumPy subsetting and slicing. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, and then this is the next column squares, so 0.1 is 0.01, 0.04, 0.09, 0.16, 0.25, so on and so forth. And then if we look at the last kind of 6 rows, 9.5, 9.6, so on up to 10, and when you square it, you get 100. Okay, so here we are going to, I'm going to just make some true values here. And so the true coefficients will be intercept of 10, a slope of 5 for the linear component, and I guess a coefficient of 2 for the quadratic component, the squared component. Okay, and I'm also going to sample values from the normal distribution, where I didn't specify anything for the center, so it's going to default to 0. Scale 20 means we're going to just basically have a standard deviation of 20. So 95% of values will be between negative 40 and positive 40, and then almost 100% of values will be between negative 60 and positive 60. But anyway, I'm going to sample 101 of these values from the normal distribution. What I will do is I'm going to add a constant, so a column of ones, and we saw that function, right? The add constant, which is just going to add a third column, but at the front, column of ones. And then the true values, so the true values of y using this will be the result of doing 10 times 5 times the first column and 2 times the third column. And then, but we're going to say the observed values of y will be the true values plus whatever random error that I have here. Is that okay? And I guess I could plot. Okay, so this is what our data looks like if we just kind of plot our x and our y. Okay. And that's what we have there. Okay. So okay. So anyway, we added the column. Okay. So now I'm going to just go ahead and fit. And here, let me just do y the first 6 values, and you know what? Actually, let's do y underscore true, the first 6 values. So the first, what is this? 10 times the 10, 5, and 2. So 10 times this, 5 times this, and 2 times this gives me 10. 10 times this, 5 times this, and 2 times this gives me that. 10 times this, 5 times this, and 2 times this gives me that. Okay, and so you can kind of see that. But we added the random noise, okay? And so when you add the random noise, the true values get obscured, right? But we're going to fit ordinary least squares regression. And so we'll just do OLS fit. We define our model. We're going to say model.fit to get our results. And then let's print the summary of our results. And so, so this is what it estimates. Our coefficients are a little bit off here. So the true value was 10, and it estimated 16.8. Okay, and it says, yeah, you know what? We're confident that it's different from 0, but the confidence interval for that intercept is 4.5 to 29.1. Right? The true value is at 10. Okay, the true value is at 10. For the slope associated with the first coefficient, it's estimating 2.16, and it's not confident if it's different from 0 or not, and its 95 confidence interval is negative 3.5 to 7.84, and our true value is 5. And then x2, the quadratic component, it estimates 2.2. The true value is 2, and it's very confident that it's different from 0. And this is, this is the confidence interval for what this coefficient could be. Okay. Overall, we get an R-squared value of around 0.924. and other kinds of stuff here. When you have the results, we're going to finish early today. You can get pretty much anything in this table. Okay, it's printed in this table, but like if you need to use the value for something else, okay, you can kind of get these things. So if you want these parameter values, 16.85 and 2.16 and 2.2096, you can just call results.parameters, and it will provide a list of those actual values. If you need the r-squared value, here our r-squared value is 0.924, and here it is, 0.924, with more decimal places of precision. There is a whole bunch of these different things that you can pull, directory results, and pretty much all of these things. I don't know if I know, like the FP value, sure, fitted values, F value, like results.f value. Which one is that? F statistic, 596.2, right? And then the probability, is it FP value? No, I forget. Well, anyway, you can kind of get pretty much anything in this table that you want to extract is available in the results, okay? And you can call it directory results. Now there's a method where you can say, all right, I want all of my predictions, okay? So we can say get all the predictions, and so it's going to tell you what did it predict for each of these 10 values, or each of these 101 values that we have. And so I can say, and when you say, all right, get the prediction, it creates a prediction results object. There's a method called summary frame, and the prediction results summary frame contains all the values, right? So we have 101 rows, and these are the predictions for every single value. And not just the predictions, but it also gives you, okay, what's the standard error on this thing? What's the confidence interval, the lower and upper bound for the confidence interval for the mean, as well as the confidence interval for the prediction intervals, right? So you have the confidence interval for what the mean is, and then you have the kind of the prediction interval for like where your predictions could end up being, right? So the prediction interval is much wider than what the mean value is. So anyway, here I will extract out basically the prediction intervals. So we're going to do the prediction.ols, we'll call the summary frame, and then we're just going to extract out this column, obs ci lower and obs ci upper, and that's going to be kind of our interval lower and interval upper, and then we'll put them all together into a single plot. So we're going to create just a figure. I'm going to plot, are we able to read plotting code? It's I still have a preference for ggplot, but anyway, so this is, this will create a scatter plot x, y. O will be the symbols that get plotted, and that will be the data. And then we have x and the true values. B will make it in blue, okay? And then we'll do results.fitted values. So that's basically just the prediction results, but just also the mean of this thing. Or we can just do results.fitted values. And this will put them in red, and the dash dash will be red with a dashed line, red dashed line. And then we'll have we'll plot the upper and lower bound of the prediction intervals, R with a dotted line, and then we're going to add a legend in the best location for the legend, and there we go. Okay, so the true values are in blue, and our fitted prediction line is in red, And we see we did a decent job. And then our prediction interval is this dotted line, which also pretty good. And yeah, we can see that most of our values fall within the kind of the prediction interval, which is what we want to see. Okay, and that's that. Okay, so this is stats models again. If you are interested in trying to do kind of traditional statistics with Python, stats models is the way to go, and your best resource will be to kind of look at your best resource to learn is the internet, really. To look at the documentation, the examples. The examples are pretty good. They're pretty sparse in terms of like what like the description. So you kind of have to just pay attention to every single line and read through every single line to kind of learn and understand. And then I mean, of course, Stack Exchange. There's lots of good questions and stuff on like, how do I figure out this kind of thing? Usually with people pointing out where to find the answers. Okay, let me go ahead and give you your last two view quiz answers for today. Last two view quiz answers are the letters C and E. C as in cat, E as in elephant. C as in cat, E as in elephant. Okay, and that's all I have planned for today for covering stats models. And with that, we'll call it a day, and we'll see you guys on Wednesday.